All right, hey crew. So we are gonna do this worksheet right here today. This is the VSEPR lab. Everybody calls it VSEPR, but really it's like VSEPR. When we get down here for the number of bonded groups and number of non-bonded groups, we're gonna cross it out and just write the number of lone pairs because that's how we did it in class. We're not gonna build a model kit and we're not gonna sketch it in 3D. That's just, we have too much to do. We will, however, talk about the hybridization and if it's polar or non-polar, okay? And we'll also talk about all these up here. Okay, so let's go ahead and get started. To remind you, we talked about two different ways of drawing Lewis structures. Okay. The first way is, let's look at carbonate. The first way, let's call it the long way. Okay, it's just the long way. So in order to do this, the first thing we do is we add up the valence electrons. So it has 2 valence electrons from this. So whatever the charge it is, that adds an extra electron. This 2 negative is essentially saying, hey, you got 2 extra electrons. So we have to add those in. Carbon is in the 4th column, therefore it has 4 valence electrons. And oxygen is in the 6th column, so it has 6. Okay, this is 18, 20, 24 total electrons. Okay, then we put the carbon in the center. We gave everything we bonded everything. The carbon is in the center because it's the least electronegative thing. And then we went around and we gave everything an octet. Okay, so now the carbon is 2, 4, 6, 8. Everything has an octet, right? And we're like, oh, that's so pretty. But then when you go to count up the electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I got 26. I have too many electrons on there. So if you have too many, remember we crossed out a lone pair from 2 adjacent atoms and we drew a bond between them. You could have done that for any of those oxygens. So really, we end up with this carbon, oxygen thing with the double bond. Cool? Okay, so this, at the end of the day, that's what it would look like. I just wanted to make it look prettier. We'd put it in brackets. We'd put a 2- on the outside because that's its overall charge. All right, this thing would resonate. Its bond order would be 1 1/3, but that's not for today's lecture. Okay, that was the long way. It took a while. Now we do the shorter way. The long way works pretty much every single time. Okay, the short way doesn't always work, and the reason it doesn't always work for things in the 3rd or below the 3rd row. So if you're in the 1st or 2nd row, oftentimes the short way will not work. You just have to make sure that things don't break the octet. So let's do this. Ready? We said that because carbon is in the 4th column, remember the objective of all these things is to be like a noble gas in the 8th row. Or 8th column. So if it's got 4 valence electrons, it wants 4 more to be like a noble gas. Nitrogen wants 3 more to be like a noble gas. Oxygen wants 2 more. Fluorine wants 1 more. So what that tells you is that carbon likes to have 4 bonds, right? Nitrogen likes to have 3 bonds, and you have to give it an octet. Oxygen likes to have 2 bonds, because it just needs 2 more. And fluorine likes to have 1 bond, right? In these situations, the formal charge of all of these will be 0. Formal charge, just to remind you, equals the number of valence minus the number of sticks minus dots. Okay. So in all these situations, if you took the number of valence electrons that nitrogen has, for example, minus 3 sticks minus 2 dots, you get a 0 formal charge. But we also said that in these things, especially the ones that have oxygen, that oxygen, when it's double bonded, it's 0, but if it's single bonded, like this, it has a -1 formal charge. Okay. So let's go back, and with that information, see if we can figure out the shorter way. So again, we're lose CO3, 2-, aka carbonate. Okay. Carbon's in the middle, and we're gonna bond it to oxygens. But this 2 right here, this 2 negative, tells us that 2 oxygens must be single bound. Because each oxygen has -1, and remember the formal charge has to be on the most electronegative thing, which in this case is oxygen. The other oxygen, therefore, if this is -1, and this one's -1, that's -1 plus -1 plus this one should be 0, the other one should be 0, for them to all add up and equal -2. So for this carbon to be a 0, it needs 2 more bonds, and that's really convenient because for oxygen to be 0, it has to have 2 bonds. And that's a much faster way of drawing it. So -1, -1, this has a 0 formal charge, that has a 0 formal charge. And you can check, you could say 4 valence minus 4 sticks minus 0 dots equals 0. Okay. So that's why this is the longer way where you count all the valence, you figure everything out, or the short way is you just kind of put things together. We're going to focus mostly on the short way today, but there might be times when we come across the long way. Okay, again, the long way tends to be these, and the one situation I can think of where the long way or where the short way fails is nitrate. All right, and maybe we can talk about how to do nitrate here in a bit. Okay, let's do this. So because this is such a small little chart, I'm just going to do kind of everything a little bit big over here, and then you can fill it in on your own over here. All right, so in looking at this periodic table, we said boron over here is in the 3rd row. It likes to have 3 things, 3 bonds, and beryllium over here likes to have 2. And it's good to remember that those 2 are exceptions. These, again, this one wants 4, 3, 2, 1, but these can have less than an octet really quite easily. Okay, so let's start with beryllium chloride. The number of valence electrons it has is 2 plus 2 times 7, which would be 16. Now it says draw the best Lewis dot structure. So we already know beryllium likes to just have 2 bonds. It doesn't need an octet. And then we'll add the chlorine. And then we can put the dots around the chlorine to give it an octet. And let's count and see if we got 16. 2, 4, 6, 8, 10, 12, 14, 16. Great, we do. The other way to do it, which would have been just as fast, is check the formal charges. That's a formal charge of 0. That's 0. This one therefore must be 0 to give us this. Beryllium has 2 valence electrons minus 2 sticks minus 0 dots equals 0. So no matter what, we end up with this structure right here. Now it says total number of groups on the central atom. Hopefully you agree that that is 2. So remember, electron group can be a single bond, a double bond, a triple bond, or a lone pair. All of those things count as what we call an electron group. Right? So then it's electron geometry. Remember, these 2 things are trying to get as far away from each other as possible. So it's electron geometry, has to be linear. Its molecular shape find this fascinating. Okay, so I better do a better job here. Groups of electrons is 2, and because it has 2 electron groups, its electron geometry is linear. The next question should actually say lone pairs. And the amount of lone pairs that this beryllium has is 0. Now I gave this to you in class, but you can see right here, we have 2 electron groups. Remember, let's just say groups. Okay. And this is the number of lone pairs, so it's got 0 lone pairs, 2 electron groups, it has to be linear in 180 degrees. So its molecular geometry, aka its shape, is going to be linear as well. So anytime you have 0 lone pairs, the electron and molecular geometry will be exactly the same. Okay, next it asks about the hybridization. So to remind you, we did S, P, 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 D, 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 D. So an S, 3 Ps, 5 Ds, just like when we're doing electron configuration. And its hybridization, you would just look at how many number of electron groups it had. It had 2. You underline the S and the P, and that tells you its hybridization is just sp. Then last but not least, it asks, is it polar? Okay, so each individual bond would be polar. I'm not going super far into it, but I'm going to draw the dipoles because this video has got to be short at some point, shorter than longer. All right, so we have a dipole going this way, where the chlorine's pulling electrons. Remember, it's electronegative. This chlorine's electronegative, pulling electrons this way. But if you have somebody pulling this way and somebody else pulling this way, don't they cancel each other out? So its polarity here is non-polar. All right, let's move on to the next one. I might reference this a lot. So next we have NH3. So N is one of those things in the third row, or it's in the second row, so it's below the third row, that we have to be a little bit careful about, and just make sure we don't give it more than an octet accidentally. So hopefully you agree there's an N that has to be bound to H's. This has 0 formal charge, that has 0 formal charge, that has a 0 formal charge, so this nitrogen has to have a 0 formal charge. There are 5 valence electrons in nitrogen, minus 3 sticks currently touching it, minus how many dots would give us 0? Hopefully you agree. That's 2, and that's our structure. Now, to remind you, these are 3-dimensional shapes, right? We did them in class, and we're like, hey, this looks like an X. In fact, I really should go get a model kit. I'm going to go downstairs and steal it from the person using it, and I'll be right back. I am back. Okay. So again, these things are 3-dimensional structures. So when we're figuring out the electron geometry, the first thing that we're going to have to do is look at the total number of groups of electrons and ask how those things get as far away from each other as possible. Hopefully you agree there are 4 number of groups on the central atom. Okay. And that its electron geometry is therefore tetrahedral, but let's talk about what that means. So if you look at all of its electrons, you have some going this way, this way, this way, and that way. And in class we said it's kind of like an X, like I'm standing here, but my arms are twisted, pointing out the 2 opposite directions. So we're looking at all of these electrons, this way, this way, this way, and that way. Okay. So its electron geometry is again the shape that we call tetrahedral. But this thing also has 1 lone pair on it, right? And that what that lone pair does is it kind of pushes these things down a little bit, right? We said that this would be less than 109.5 bond angle in class. But another important thing to think about is that when we're figuring out the molecular geometry, aka the shape, we want to focus on just how the atoms look, okay? We're not looking at the electron groups anymore. So hopefully you agree this looks like a pyramid, right? Look at it, so pyramidy. If I put it up, it looks like a pyramid, and there's a triangle on the bottom, and that's why its molecular shape is trigonal pyramidal. You can also look at this thing that we did in class and say there's 4 electron groups and 1 lone pair, and you'd get this thing right here. Okay. All right, onto its hybridization. That goes back to the 4 electron groups. So the SPPPP, I'm only going to do this for the first few of them. Because there's 4 things, we underline 4, and we get an answer of SP3 as its hybridization. Okay, then we get to the polarity. Okay, on the periodic table, as we go up and to the right, things get more polar. Okay, we talked about cannot clean out fridge. Nitrogen is more polar than hydrogen over here, okay? Because nitrogen is more polar than hydrogen over there, this nitrogen is going to be pulling electrons toward it. Now you might look at those things and think that maybe they cancel each other out, but don't forget that the shape is actually this way. So you have electrons going this way, and this way, which means that overall there's polarity going up in that direction. So this would be polar. All right, moving on to the next one. PCl5. Okay, n equals 3 or below, so PCl5 is going to be fun and straightforward to draw. We draw P, we draw 5 Cls, and we make sure those Cls have octets. Okay, and then again we look at the phosphorus and we say it's got 5 valence electrons as the 5th column, minus 5 sticks. So how many dots does it need to be 0? Hopefully you agree it just needs 0, so we don't put anything on it. We are done this PCl5. Now it wants to know the total number of groups on the central atom. 1, 2, 3, 4, 5. So number of groups is 5. All right, then we want to know the electron geometry. Okay, because it has 5 different things. Let's see if I can make it for you real quick. You can go to this. Because it has 5 things, it's got 3 kind of in this triangle, like this, and then 1 sticking out here, up and down. So it's got 3 and then those sticking out, up and down. Let's see if I can find one with 5 for y'all. It's gotta be in here somewhere. I miss my old model kit, y'all. Mine got taken. I had it and then somebody came in the classroom and took it. Okay, I don't know. Shouldn't say 5. So, anyway, it's got 3 that are like this, trigonal planar, and it has 1 coming up and 1 going down, okay? And we call that thing trigonal bipyramidal. So its electron geometry is trigonal bipyramidal. The next question asks about the number of lone pairs. Hopefully you agree this phosphorus has no lone pairs. None on it. We don't worry about the outside ones, just the center ones. And then we gotta look at the molecular shape or the molecular geometry. Anytime there's no lone pairs, these two will be exactly the same. So this is also trigonal bipyramidal. Okay, then we get to the hybridization. So for the hybridization portion, because there's 5 electron groups, as we go through our SPPPP, we go through 1s, we go through 3 p's, we go through 1d. That's 1, 2, 3, 4, 5. Okay. Then it's polar or non-polar. So let's look at this thing. Okay. Looks like this. You have this, again, this triangle like this, and you have one thing coming up from it. Do a better job here. You have one thing coming up from it like this, and then on the other side is one thing coming out from there. So I'm trying to make it flat because this triangle right here would be flat. It would have been plane. It's like trigonal planar. Okay, so you got this thing in the plane, you got one coming up and one coming down. Okay, they are all equally pulling each other. So if this is the chlorine that we just drew, it's got a chlorine pulling it this way, chlorine pulling it that way, chlorine pulling it that way. It has one pulling up and one pulling down. So there's an equal and opposite pull for every single one. Even though those individual bonds are polar, the overall thing is non-polar. They are all equally and opposite pulled. Or I thought, like, in case anybody's having trouble picturing that, my dogs have a toy and it looks like this. I have 3 dogs. So when one pulls this way, one pulls this way, and one pulls this way on the toy does not move. So if you have equal and opposite pulls, then it's not going to be polar. All right, moving on. Let's keep it going. VSEPR. Okay. S, n equals 3 or below, so we can do this quickly. We're going to draw an S, 4 Fs, sulfur tetrafluoride. I just saw that it said name the compound. We haven't named any of these. Okay, so we give them all octets, all these outside ones, and then we worry about the middle. If that has a formal charge of 0, that's 0, that's 0, that's 0. What must sulfur be? Hopefully you agree it's 0 for them to all add up and equal 0. So sulfur currently has 6 valence electrons. It's got 4 sticks attached to it. So it needs how many dots in order to be 0? Hopefully you agree it needs 2 dots, and that's where we go, boop, boop. And that's SF4. All right, so when we go to figure out the number of electron groups, you got 1, 2, 3, 4, 5. So our electron groups is 5. Okay. We know, therefore, that the electron geometry is going to be the same as the last one, trigonal bipyramidal. I really wanted to find you one of these to do it. Okay, well, anyway, trigonal bipyramidal, and then the molecular, or the lone pairs, though, on this one is just this one right here. So, you know, that's going to change things, okay? So now, essentially, before, when we had 5 groups, it was 1, 2, 3, and then 1 pointed up and 1 pointed down. Now it's 1, 2, 3, and a lone pair right here, okay? So these 3 are all in a plane. This one, and this one should all be in a plane. If I had the appropriate model kit, I could show you. They're all like this. And now it has a lone pair right here, okay? And that one's pointed out. All right, once you have that, 5 things with 1 lone pair. Kind of wish I could show it to you. Oh, no. I'm so mad this model kit doesn't work. Okay, so once you have this, you get something called a seesaw shape, which if everything was working perfectly, I would be able to flip this over and show you that it actually twists like a seesaw. And that's why it's called a seesaw. So over here, you can kind of see those are the feet. One's coming out, one's going in. And this is the seesaw. It goes up, down, up, down, up, down. Okay, so it's kind of like, and that's the molecular geometry for this. Its hybridization didn't change from the last one. It's got 5 electron groups, so it's sp3d. Let's talk about its polarity. Now, even though you have equal and opposite pole of the dog toy that I talked about, now you don't have an atom on the bottom right here. Instead, you had this lone pair, okay? So these are all canceled, but here I have something pulling up and nothing pulling back down. So this would be polar. It's got unequal pull. Okay, moving on. Just gonna save some paper here. All right, we're going to do VSEPR, which we've done in class a lot. Actually, we've done it so much, I'm going to skip it. We're going to do CH4, which we also did in class. So CH4 is a carbon with 4 hydrogens. I can tell already that's the correct structure because I know that carbon likes to have 4 bonds, hydrogen likes to have 1 bond, all of these would have a 0 forward charge, and therefore this is correct. Okay. The total number of electron groups around that carbon is going to be 4. The electron geometry is going to be tetrahedral. Right? It's going to look like this, where essentially you have like, there's the feet at the bottom, and the top you got one coming up, one going down. It has 0 lone pairs, so therefore its molecular geometry also has to be tetrahedral. Its hybridization, because it had 4 electron groups, you go through the first 4 and you just get sp3. And then when asked if it's polar, remember that a carbon-hydrogen bond is a non-polar bond. So all of these have the same exact electronegativity, so there will be no uneven pull of them. So it's going to be non-polar. All right, moving on to the bromine. BrF3 looks like. Okay, so this looks like a really fun one. I haven't done it before, so let's figure it out. We got a bromine, we got 3 fluorines. We know the overall charge has to be 0, right? Because there's no charge written up here. So if that's 0, that's 0, that's 0, bromine must be 0. Bromine has 7 valence electrons, has a 7 column. It has 3 sticks, so how many dots does it need to be 0? Hopefully you agree it needs 4. So 1, 2, 3, 4. Okay. So number of groups looks to be 5. Okay. The electron geometry, if it's 5, we know already it's trigonal bipyramidal. Okay, its molecular shape, its lone pair has 2. So let's look at its molecular shape. Okay, it's got 3 things. Killing me. Yeah, I don't know. The one that I used in class is gone. I probably left it in class. So it's got 3 things on it, and it ends up looking like this. We called this shape trigonal planar because it's got 3 things in it, 1, 2, 3, and it happens to all be in a plane. Okay, but when we go look at this, over here, so it's got the 3 things like this, and it has 1 up here and 1 down here, right? So when if it's trigonal bipyramidal, 1, 2, 3, 4, 5, and it has 2 lone pairs, where it's taking those 2 lone pairs is from here and here. So you're left with this plus 1 up and 1 down. Okay, so 1 up and 1 down like this. And hopefully you agree that looks kind of like a T. T, see it? Yeah. And that's why it's called a T-shaped. So that's how we get this thing right here. So it just pulls 2 off and you get this thing, which is a T-shape. All right, its hybridization still hasn't changed. SP3D2, or excuse me, SP3D, because there's 5 things. 1 S, 3 Ps, and 1 D. And let's talk about its polarity. Hopefully you agree. If you've got this T-shaped thing here, it's looking like this. Okay, you don't have equal and opposite pole in every direction. One's pulling this way, one's pulling this way, but this one that's pulling up right here, that I'm hitting with my pinky going this way, that one doesn't have any counteracting pull that way. So this thing would be polar. Right, let's keep moving. On to SeO2. Ooh, this looks like a good one. Okay, so I lost my periodic table, but you can see Se right here has 6 valence electrons, and each oxygen also has 6 valence electrons. So we'll need that in mind when we do formal charge, but it falls below the 3rd row, so we can have more if we need to. So we're gonna do Se. We know that there's 2 oxygens in here and there's no overall charge, so that probably means each of them wants to be doubly bound. Remember, to get a 0 formal charge, they want to be double bound, like that. And now we just look at selenium. We know that it has 6 valence minus 4 sticks touching it right now, so then it just needs 2 dots to equal 0. So let's give it 2 dots. Boop, boop. Cool. Okay, so when we go to put that thing together, it's going to look like a flat triangle, electron geometry wise, because it has 3 electron groups. 1, 2, 3. Okay, so it looks like this. So its electrons are all in a plane. So its electron geometry is going to be trigonal planar. It's a triangle all in a plane. Okay. Its number of lone pairs, though, is 1. So its molecular geometry is what this looks like once I remove this one. So what does that look like? Hopefully you agree that sucker looks bent, right? And you would be right. Its molecular geo is bent. Its hybridization, there's only 3 things on it, so it's an sp2. 1 S, 2 Ps equals 3. And then we ask if it's polar or not. This is a pretty important concept. Okay. Even though we draw it like this, and it looks linear, doesn't it? So it looks like the pole here is equal to the pole over here. The truth is, it's bent, meaning the pole down here does not counteract the pole that's going this way. So oxygen is more electronegative, so it's pulling this way, it's pulling that way. So overall, the pole's going down, pulling this thing down, and it would be polar. So anytime it's not all canceling each other out, it's going to be polar. BF3 is next. That's the piece I'm really missing in my model kit. Something special about boron, remember, it can have less than an octet. Really anything can have less than an octet, but this has less than an octet and keeps a 0 charge. So this is going to be a different one than most. We already know that boron wants to have 3 bonds. Okay. Let's give the fluorines the octet though, because they need it. They really want it anyway. Okay. And we don't need to do anything else. But we could check this all because remember that has 0, that's 0, that's 0. Let's look at this boron. It has 3 valence electrons minus 3 sticks. It needs 0 dots in order to equal 0, and that's why this structure works. All right, let's talk about the number of groups. Hopefully you agree it's got 3. So therefore its electron geometry, I don't know why I'm writing. Its electron geometry is going to be trigonal planar. All 3 things in a nice little plane like this. It has 0 lone pairs. Its molecular geometry, therefore, must be the same. Trigonal planar. Its hybridization, because it has 3 things, is going to be sp2. And is it polar or not polar? Hopefully you can kind of see this. This is the dog toy I was talking about. Fluorine's pulling it this way, and this way, but overall they all counteract and cancel each other out. So its polarity would be non-polar. All right, let's keep it going. We're getting there. We have XeF2. Oh, this one's gonna be cool. Okay, let's do it. So we have a xenon, and we've got 2 fluorines. Okay, and then we know these all need that. And then we look at the xenon here. It has 8 valence electrons. It currently has 2 sticks, so how many dots does it need in order to be 0? Hopefully agreed it needs 6. 1, 2, 3, 4, 5, 6. So it looks like that. Really, well, let's keep going. So the number of groups is 1, 2, 3, 4, 5. We know that electron geometry, I don't know why I keep writing EQ like equilibrium. Its electron geometry is going to be that trigonal bipyramidal. But its lone pairs are going to be 3. Remember the trigonal bipyramidal was like this, except there's one sticking up and one sticking down, right? If we removed all 3 of these and had only one sticking up and one sticking down, wouldn't that be like linear? And that's exactly what you get. So its molecular geometry is linear. You can look at this table and see. We had this beautiful triangle here, here, here. One sticking up and one sticking down, and we removed all the triangles, so it's just these 2, and it's just like a linear thing. Okay, now it says hybridization. Again, you do build the hybridization off of the number of electron groups. It would be sp3d. And is it polar or non-polar? It's a line, so if you have a line, you have one thing pulling this way, one thing pulling the opposite direction, and it would be non-polar. Two more, y'all. We can do this. SF6. Okay. S is a third or below, so it can take more than an octet. We're going to draw an S. We'll put 6 Fs on it. And when we go to look at the formal charges, remember they all must add up to equal 0 because the overall structure is 0. That's 0. That's 0. That's 0. That's 0. That's 0. That's 0. Sulfur has to be 0. Sulfur has 6 valence electrons. There are currently 6 sticks touching it, so it must need 0 dots in order to equal 0, and that's what we already have, so it's good the way it is. Electron groups. I see 1, 2, 3, 4, 5, 6 groups on that sulfur. So therefore my electron geometry has to be what we call octahedral. think I actually have the oh, I do. I actually have the octahedral thing. Let's do it. Bad. Octahedral is weird because you hear oct and you think 8. That's because if you actually really drew it out, you could get like 8 faces of a triangle in here. Maybe I can show it to you on this. If not, look up a picture and it's worth it to kind of visualize. Okay. I need one more. Sweet. Okay. So this is what it looks like. It's called octahedral because if you built a triangle here and here, that'd be 1, 2, 3, 4, and you could do the opposite on the bottom, 1, 2, 3, 4. So you get 8 different triangles out of it. All right, so this is our octahedral shape. You got this X in the middle, and then it's like being stabbed. So you got 1, 2 things going through it. Okay. So the number of lone pairs this has is 0. So we already know its molecular geometry must also be octahedral. Its hybridization. So we're going through 1 S, 3 P's, and 2 D's in order to get through 6 letters. And then polarity-wise, all of these are the same thing. They're all fluorines. So hopefully you agree. If this one's pulling back. And if this one's pulling back. This one up here is pulling, this one down here is pulling back. So they all have counteracted force. So this would be nonpolar. All right, last but not least, IF5. Okay, so for IF5, we have an I, 5 fluorines. This has 0, that's a 0, that's a 0, that's a 0, that's a 0. So what does I have to be in order for this whole thing to be 0? Hopefully you agree it has to be 0. Iodine currently has 7 valence electrons. It's got 5 sticks touching it, so it must need 2 more dots in order to be 0. Now its number of groups is 5 bonds plus those 2 lone pair gives me 6. Therefore, its electron geometry is also, once again, octahedral. All right, but the number of lone pairs it has is 1. In other words, it would have looked like this, but it popped one of these off and put a lone pair right here. Okay. So it's no longer that. Its molecular geometry. If I take this lone pair off and kind of show you, it's going to help. Has a square bottom and something on the top, so it kind of looks like a pyramid. Square bottom, something on the top, making it look like a pyramid. Square, pyramidal. It's going to be its molecular geometry. Hybridization. It's got, again, 6 things, so it's still going to be the sp3d2. And then whether it's polar or not, all of these, this one and this one cancel, this one and this one cancel, but this one going up has nothing to cancel the pull going down, right? So it's pulling this way, but there's nothing to cancel it in the opposite direction, and that's why this thing is polar. I think we did all of them, but XEF4, which you should be able to do on your own because we did it 3 times in class. Maybe only twice. I might be exaggerating. So anyway, y'all, I will see you later. Have a great day, and I hope this helps. Bye.